What's up, guys? Mr. Stark here, and what I want to go over in this presentation, and it's going to be a three-part video. So right now you're going to see part one, then there'll be part two, then there'll be part three. In the article 210.4 ABCD in the National Electrical Code, it talks about multi-wire branch circuits. And they don't talk about the dangers of the multi-wire circuit because we read the article and we don't really see the underlying danger if you don't apply the four major provisions of installing a branch circuit for a multi-wire correctly. We're going to go over those in a second. In this picture, you're going to see it's your normal three-conductor, three-wire 120/240 volt single-phase service. And this picture that you're looking at is essentially a diagram of what a transformer secondary would look like. And I simply connected two light bulbs to each 120 volt phase. So this picture is very simple. It's not showing the panel or the circuit breaker or any switches that would be in the house. I'm going to prove a point with this drawing in a second. And all houses have this type of service. You have 120 volts from one of the hots to neutral, or your grounded circuit conductor, which is bonded at the main service, which becomes 120 volts to ground. And you have the same thing on the other hot phase from 120 volts to ground, and you're sharing that neutral path for the the complete circuit for the way home. Between the two hot conductors, up here and up here, you have 240 volts phase to phase. So this is important to understand this because we're in electrical theory, and really what you're looking at here is two circuits that are in parallel with each other. So right now we can kind of see the similarities in the drawings that we're doing in class or at home. This is a parallel circuit that you're looking at, and we'll talk about what the danger is behind that. And then the next part for my experiment in my video, we're going to be wiring two plugs and two lights. The circles represent lights, and of course the plug is the plug. And I have a 14-3 that leaves a panel. It's connected to a 2-pole 15 amp breaker. It shares the grounded circuit conductor or the neutral path home. I have that drawn in as blue. You'll also notice that I have the neutral conductor, or the blue in this case, tied onto the switch because what I want to do is simulate an open neutral. So an open neutral on a multi-wire circuit poses an extreme danger to the devices connected or the load connected, and anybody that might be in that area. We pose a real threat. You're going to see the threat in a minute because we experience what we call voltage drop. So what I'd like to do is when we see the next video, my lab, the hard wiring in the lab looks like this picture. I blew up the single pole switch so that you can clearly see that the whites are tied onto the switch. We would never do this, but I'm doing this so that I can safely open the neutral under load. I need to open the neutral under load so I can demonstrate we're going from a parallel circuit to a series circuit and what actually happens. There's a pretty good mathematical computation on Mike Holt in the capacitor in Article 210, multi-wire branch circuits. But this I'm simplifying so you can visually see what happens. So we'll get back to this picture in a later video. But for now, what I want to do is set you up in front of this service here. And I'll try to get in a little bit closer and get a second to make sure everybody can kind of see what's going on here. Bear with me. So now in this case, if I was to kind of go over what is happening here, my picture, I'm trying to show you, I'm trying to open the neutral. So what I'm actually doing is I'm putting a switch on the neutral in my lab. That's the first step. And we never want to rely on the continuity of a removal of a device to open the neutral. So I'm going to pretend that this is closed right now, as it should be. We should never have an open neutral on a multiwire. But what you can see here in this graphic is we have two 120 volt circuits, and they each have their own path back to ground, so to speak. So if I was to, let's just pretend this is circuit 1 and this is circuit 3. Well, circuit 3 is on, and it too shares that neutral for a path home. You can clearly see if I put a switch in here, whatever, this would be its own circuit, and this would be its own circuit, both relying on the grounded circuit conductor back home. Now, if we take this illustration a little bit further, we take it a little bit further. Let's erase this for a second. Do the same thing up here. Let's get rid of that red line. If I was to open the neutral, here's the danger. Now, what happened is I set up a series loop. Now watch the path of current flow. So pretend that this neutral is no longer here. If you want to illustrate this better, by opening the neutral, essentially what you're doing is this. Now, our path for current flow, we're getting the full 240 volts through both loads in a series loop. We have one series circuit, and remember, voltage in a series circuit is additive. 120 plus 120 gives me my 240, which is my phase-to-phase voltage. So now what's going to actually happen in my experiment, depending on what my resistance is across these two loads, is going to dictate how much voltage I drop across each of the resistors, which in this case is going to be light bulbs or a TV if I plug a TV in. So I'm just saying hypothetically, I haven't done the math yet. Let's say this resistance is 100 ohms and this resistance is 10 ohms. If we did a little bit of Ohm's law and if we calculated, we may hypothetically, don't correct my answers on this, I may drop 180 volts on that resistance, and I may be, what's left from 240 is 60 volts. So really, it depends on your resistance as to how much voltage you're going to drop across the load. So we're going to experiment this in lab. We're going to put in a, let's just say a 40 watt light bulb and a 100 watt light bulb. We'll measure the resistance, and you're going to see that one light bulb is going to be super bright. It's getting almost 200 volts, and the other one is getting next to nothing because we dropped a certain amount of voltage across that load. So always keep in mind that if you open the neutral in a multiwire, you're actually creating a series loop on what was normally a parallel path with 120 in each of those. And let me illustrate that one last time. The right way would be this neutral would be tapped at the center of the transformer. This would be neutral. You would have no switch in there. And then you'd have one 120 volt circuit in parallel with the other circuit. You'd have 120 going to that load, you'd have 120 going to this load, and you'd have no problem. So how does the code come into play? Well, 210.A, B, C, and D tell you how to properly wire it, and each one of these is based upon theory. So the theory in this case is really this. Grouping, same panel board, and this takes a while to explain each of these, so I'll probably continue it in the video. Simultaneously disconnect both ungrounded circuit conductors. So that means two-pole breaker. And then last but not least, and there is an exception to this rule, only feeds line to neutral loads. Now, if I'm going into this extremely brief, grouping means that if you have a 14.3 coming into a panel, and if it's coming into a Romex connector, and I'm going to illustrate it like this. Pretend that you've got a Romex connector and there's a 14.3 coming into it, black, red, white. Well, that connector really lets you know that that's the only way that conductor can come in through that connector. There's only one wire in that connector. So that's already grouped. If I had a bunch of whites and reds and blacks coming out of a conduit, and if there was a multi-wire circuit in there, I would have to find the neutral that belongs with, let's just say, circuits 1 and 3. 1 and 3 in your panel board are going to be stacked on top of each other. There's my 2-pole breaker. But circuit 1 is actually connected to this busing. Circuit 3 is actually connected to this busing, and they're opposite phases. This is very important to the theory that's going on in here. In either event, that neutral that's shared between circuit 1 and 3 needs to be individually grouped, tie-wrapped, or string tagged to let it be known that that neutral belongs to circuit 1 and 3. You could use numbers, you could use a string tag or tape, but that grouping absolutely has to happen. Somebody goes into that panel later and starts messing stuff up. If they end up taking what used to be 1 and 3, and then let's say put 3 over here on the same phase, which would be circuit number 2, now you're going to overload that neutral. So if you don't group it, you could make the mistake of overloading the neutral if somebody goes back in that panel and messes it up, or more importantly, not knowing that there's still current coming back on that neutral if they turned off circuit 1 and circuit 3 was still on. So this is based on theory, so nothing bad happens. They all must originate from the same panel board. I can't take circuit 1 out of one panel board and circuit 3 out of another panel board. I have to bring that neutral to they all have to be from the same panel board. We don't want to make the mistake of putting circuit 1 on, let's just say, phase A, and circuit 3 on phase A. Then you're going to have double the amount of current come back on that neutral. We want to avoid that at all costs. So once again, that is theory. Common sense. Simultaneously disconnect both ungrounded conductors at the same time. Well, let's just say that you ran a 14.3 and you put the black circuit on circuit 1, then you went way down here on circuit 30 or something, and you put the red circuit of the 14.3 on there. Well, we need to simultaneously disconnect both ungrounded circuit conductors at that source. So let's say I think circuit 1, I turned off circuit 1, and then I go into that junction box and I feel that it's off. And I'm like, okay, we're safe. But now I'm in that junction box and I'm still getting current from circuit 30 because red is on. So we want to make sure that both of these are in line, 1 and 3 or 2 and 4, for theoretical reasons. If you're not trying to avoid a shock hazard, we'll put here, or the theory of overloading the neutral again. So notice, theory, theory, theory. Last but not least, line to neutral loads. There are exceptions to this. I can feed my range, my clothes dryer, I could feed 240 volt equipment on a multi-wire. Those are the exceptions. But in general, I can only feed a line to neutral load. So line to neutral, hot and neutral, 120 volts to ground. And I could do it that way. And once again, this, on a later explanation with more drawing, is based upon theory. So when you go to 210.4 and you read multi-wire, and then you read A, B, C, and D, and if it goes over your head, understand that this is all based on you putting your hands on this work. You're going into the panel with that Romex. You're tying it into that breaker. All of this is based on you tying it in correctly so that we don't have any theory problems in the field with possibly overloading a neutral or anything of that sort. I will get back to this on another video. This is just a preview of what we're going to be doing with this in the lab. We're going to actually try to simulate blowing up light bulbs or a TV by opening the neutral and creating a series loop. Hopefully this helps. I'll see you at the next video.